so let's start with the 12.4. And then after these two sections, we have one section left on Monday. And that's the course. So what we're going to start with in 12.4 is solving exponential equations. How did I know when I looked at something that it was an exponential? The x, where was the x? It was in the exponent. The exponent had the variable in it. So that's how we know we have an exponential, because usually on the final exam it's just going to say solve the equation. And you're going to have to look at it and know how to solve it. And you can usually do that just by identifying what type of equation you have. So exponentials, again, have a base, and the variable is in the exponent. That's what makes it an exponential. That's how you know you're going to use the method we're about to learn. The variable's in the exponent. We don't want it there. What we want to do is we want to be able to get the variables out of the exponent. And what we use is we use this uniqueness of b to the x property that says if I can get the same base on both sides, so they both have a big 2 or they both have a big 3, then the exponents have to be equal. That's the only way it makes a true statement. If I have the same base, the exponents also have to be the same. If the exponents are different, then the values of the two sides of the equation would be different. So we're going to use this uniqueness of b to the x. And you'll see at the top, and this is not a table that you get on a test. This is just a reminder. And we've seen a lot of these numbers before. And I'm not going to give you something outrageous. Notice the table here only goes to base 5. And that's just all your powers. So your powers of 2. 2 to the first, second, third, fourth. These ones you're probably a little bit more familiar with. We've seen those 9s and 27s come up all the time in our radical work. If you're not sure, like, if you can figure out the base, what you think for one side of the equation, use your calculator and just start plugging in, like, 3 squared, 3 to the third, 3 to the fourth. If you think you should have a base 3, I mean, you have a calculator. It shouldn't be too hard. See, the highest exponent I ever even went to was 5. So there's not many options here. But what we're going to try to do is we're trying to get both sides of the equation to have the same base. Because if they have the same base, then we know the exponents are equal. And we could just drop the base. And this is how you solve, in this class, exponential equations. When you get to your higher math, there's actually a lot better ways to do this. Because it's like solving by factoring. It doesn't always work. But in the equations in here, you'll always be able to find a common base, drop the base, set the exponents equal to each other. So let's start with the most basic of examples. So notice that the two sides of the equation in example A have the same base, right? Both have a big 2. We know it's an exponential equation because I have a variable as part of an exponent. Well, if I have 2 to the third on the left side and 2 to the x on the right side, what does the x have to be for that to be true? 3, right? If I put like 2 to the third equals 2 to the fourth, it's not true. So what the uniqueness of that b to the x, the rule that we're going for is that once the bases are the same, so I get the 2's, I can cross them off and just look at the exponents. So I get x equals 3 for this one. Now they're not always that easy. Now B is still a pretty easy example. So I'm looking at 5 to what power gives me 625. Now that could be one that you could just look at, but not all of them work like that. So what we're going to try to do, you see that this is an exponential equation. What we know we want is the same base on both sides. So one side has a 5, the other side has a 625. Can you think of a common base? Something that I could raise to a power, be the same on both sides. So if you look back, this is another, when you're starting out, this is good to reference. If I look at my table, which base has both the number 5 and the number 625 in it? 5. So I'm going to use a base of 5. Okay, well the left side has a base of 5 already. So I don't need to change the left side at all. So I'm going to leave the left side as 5 to the x, but I need to rewrite the 625 as 5 to some power, because this rule only works if I have 5 on both sides. So 5 to what power gives me 625? 4. And again, if you think and you're not sure, just put it in your calculator. If it doesn't work, you'll know if you have to go up or down. But I'm not going to give you outrageous numbers. Okay, well, if 5 to the x equals 5 to the 4th, what does x have to equal? 4. Because once you have the same base, we can cross them off and we just set the exponents equal to each other. So x would have to equal 4. So this is our uniqueness of b to the x. Once we get the same base, we know the exponents have to be equal. It's the only way it's going to be true. All right, C. 3 to the x equals 1/9. Now you might be able to just look at this one. We actually looked at problems like this a lot yesterday. If I have a fraction, what's true about the exponent it came from? It's a negative. So if we're gonna go full on rules, full on uniqueness of b to the x, how could I, well, what do you think my common base might be for 3 and 1/9? 3. So the left side is already base 3. It's 3 to the x. How could I rewrite 1/9 as 3 to some power? We've got to start by rewriting it. -2. So if you have a fraction, you know that it's a negative exponent, just like we had on Wednesday. And then 3 squared gives me 9. So 3 to the -2 is 1/9. So now I have a common base. My common base is 3. And that's what we're going for with exponential equations. You want them to have the same base, because once the base is the same, we can kick it out of the problem and just compare the exponents. So we get x equals -2. Any questions so far? All right, D. D is the first one that you could not just look at and solve. 4 to what power gives me 8? Well, we know 4 to the first is 4, and we know 4 squared is what? 16. So it's somewhere between 1 and 2, which means it's going to be a fraction. But when these answers are fractions, they're no more difficult to find. What we want to do is, first thing you should do on all of your tests, your Unit 4 tests, your final exam, is try to identify what type of equation you have. Do I have a quadratic equation? Do I have an exponential equation? Do I have a linear equation? Because that's going to dictate where you go to try to solve it. So when I look at this, what stands out to me as far as identifying what type of equation I have? The x is in the exponent. Because I find that this is, and I don't remember if this is on your final this year, this is a very missed Unit 4 test question and a very missed final exam question. People look at that and they're like, I have no idea how to get rid of that x. If the x is in the exponent, it's an exponential equation, which means we need to get same base. So 4 is not going to work. In every other example, I just took the littlest number and it was our base. I need to try to think of a common base for 4 and for 8. 2. But this time, I'm going to have to rewrite both sides, not just one of them. So how could I, first I'm going to try to replace both of these numbers. We said we can get them both to a base 2. So 2 to what power gives me 4? 2. 2 squared. 2 squared is 4. But notice that in our equation, it wasn't just 4. We had 4 to the x. So you have to drop down whatever exponent was already there onto what you're adding in. That's another thing that people commonly miss. If the equation already has something in the exponent and you rewrite that side, you've got to drop the original exponent down as well. If it's a binomial, we're going to bring it down in some parentheses. And then how about 8? I want to rewrite it with a base of 2. So 2 to some power gives me the number 8. So I heard 3, I heard 4. Not sure? Grab your calculator. Just tech it. 3. 2 to the third. And now that we have the same base, what can we do with the bases? Cancel them out. Drop them off. If the bases are the same, we can get rid of them, and we know that the exponents left over have to be equal. But this one doesn't just give us x. This gives us 2x. I don't want 2x. I want x. So how do we finish solving this equation? Yeah, just divide them both by 2. So x equals 3 halves, which, as predicted, is somewhere between 1 and 2. It's actually 1 and a half. 6 exactly, but. So they don't always work out to be whole numbers. But all you have to do is look for that base that you can get them both. So they have the same base. Questions so far?
We can leave it like that. We don't put it like in decimals or anything.
No, you know. I actually prefer it as a fraction, as long as it's reduced. But this one divides evenly, so decimal would be okay. If it didn't divide evenly, then you need to leave it as a fraction. All right, E, I have 9 to the x minus 1 equals 27 to the x. So first thing I need to do is come up with a base that I can get them both to, because this is an exponential. So it's an exponential equation, so I need same base. Now the first check is always to look for your smaller number. Can I rewrite 27 as 9 to some power? All right, now I know what power gives me 27. That's 9 times 3. So think about, remember, we're thinking powers. So if I say in 3, it's 9 to the third, which is like 729. Yeah, that's 729. So 3 is not going to work, because we're not looking for multiplication. We're looking for powers. All right, so 3 is out. 3 gives me 729. That's not 27. So I can't rewrite 27 as 9 to some power. Because if you start thinking about your powers of 9, 9 to the first power is 9. 9 to the second power is 81. We're already way overblown 27. So I need to find a common base for both sides now. I'm going to need to change them both. So I think we're getting the idea now. Base of 3. I could rewrite 9 and 27 both with a base of 3. So what I'm going to start with is I'm going to start by rewriting both of the big numbers as 3 to some power. Remember, it's not multiplication, it's raised to a power. So 9 is 3 to what power? Squared. Okay, so 3 squared. But what else was in that original left side? This x minus 1. You've got to remember to bring that down. And when it's a binomial, we'll put it in parentheses. No, because the 2 is attached to the 3 in that it's replacing 9. And then anything else that was in the original problem we carry down. I mean, eventually we are going to distribute the 2. At some point we'll have to distribute the 2. All right, how about 27? 27 is 3 to what power? 3 to the 9th is 19,683. 3 to the third. Again, these numbers are going to be small. They're not going to be huge. So 3 to the third. I know what you're thinking. Again, you're thinking of the multiplication. But in terms of powers, 3 times 3 times 3 gives me 27. So I'm going to put 3 to the third here. And what else do I need on the right side? X. Got to bring down. Don't forget those originals. So are there any questions just so far on how we rewrite this problem to get that same base? And why do we need the same base? What can happen after we have the same base? Cancel them out. And then we'll be able to get those x's down to our regular equation. So let's cancel out the 3's since they worked out to be the same. So I have 2 to the 2 times x minus 1 equals 3 times x. Got to distribute the 2, so we're going to clear the parentheses. So now we're back to regular old algebra problem. So 2x minus 2 equals 3x. What type of equation is this? Linear. Yeah, there's no x squared in it. I don't think you'll ever see one of these with x squared in it. So x is to one side, numbers to the other. I'm going to bring the 2x to the right. It'll be the quickest way to solve this. You can bring the 3x over, but then you got to send the 2 back. It's more steps. So we get negative 2 equals x. So it's being able to find that same base. So once you have the same base, cross them off, you're going to have a linear equation. All right, f, 5 to the 2 minus x equals 1 over 125. What do we think our common base might be for this problem? 5. So here's a hint. If one of your bases is already reduced as far as possible, that should be your common base. So 5, I can't break 5 down anymore. 5's prime. So how could I rewrite? So we're going for a base 5. I need to think of how I could rewrite, because I don't need to rewrite the left side. Sorry, I got a base of 5. How I could rewrite 1 over 125. Well, if it's a fraction, what's true about the exponent? Negative. 5 to the negative third. So you're looking at the 125. After you've decided it's a negative exponent, you're really just focusing on 125 is 5 to what power? To the third. So it's going to be 5 to the negative third for our fraction. And then we have a common base. Once we have a common base, go ahead and kick it out of the problem. So I have 2 minus x equals negative 3. This should always be linear. You shouldn't have any more exponents in it. You might have to distribute. That's about it. Now let's finish solving for x. So I'm going to subtract the 2. So I have negative x equals negative 5. Divide by negative 1 to finish solving for x. And I get x equals 5. Which makes sense. Now you can always go back and check these because, okay, if I put 5 in for x, my exponent is 2 minus 5, which is a negative 3. So the left side is 5 to the negative third. Does it equal 1 over 125? Yeah. Now even for the funky ones, like this one right here, where it didn't work out to be even, grab your calculator, take 4, raise it, you got to use parentheses, to the 3 halves, and you'll see that you'll get 8. So you can always check these. Just make sure that both sides are the same number, even if it's not a whole number. Just make sure both sides are equal. Questions? So you have a couple of these on your classwork. So that's the really big new topic today. The other thing we're going to do in 12.4 is we're going to solve logarithmic equations. But logarithmic equations, we did some of these yesterday. Yesterday they all looked like this, where the x was on the right side. But now I'm just going to move the x around. I'm going to put it as what you're taking the log of, and I can also put it as the base. So what we want to do to solve these equations that have a log in them. If they have a log and an x, first thing to do is to rewrite it as an exponential. So who remembers the pattern for rewriting this? So we always start with our base. So the number I'm going to start with here, 2. This is what your drill would have been today if we didn't have so many snow days. So 2 to the 4th, you always skip to the other side for your exponent, equals x. So if you see an equation that has a log in it, just rewrite it as an exponential. Then we can either use the method we just finished with, or look at this one. Do I have any solving to do for x? Or is x already by itself? It's already by itself. So all we have to do is figure out what 2 to the 4th is, and we know what x is. So this is a type of equation where we end up just evaluating 2 to the 4th power. So 2 to the 4th is 2 times 2 times 2 times 2, or 4 times 4. So it's just 16 equals x. So sometimes all you have to do is evaluate after you rewrite. There's not even solving to do here. It's just evaluating. And that's going to happen if your x is what you're taking the log of. So we know that x equals 16. Now the directions, if you read them, you're like, that's a lot of directions for that problem. It says be sure to reject any values of x not in the domain of the original logarithmic expression. How do we find domains of logarithmic expressions? Also would have been on your drill today. He asked for the domain. It's the last thing we did last time. I said it's most missed drill question, commonly missed test question. What you're taking the log of has to be greater than 0. Now, for us, for the equations, they'll always be in the domain, but just make sure you remember how to find the domain. But our answer fits. 16 is bigger than 0, so we're okay. But that's what that question means when it says that. It's make sure it's in the domain, because there are values that don't work. If the answer was negative, we'd have no solution. Now, we're not going to get that fancy in here, but just remember how to find the domain for these. Now B, we have a natural log of some number equals 3. So natural log. So we talked about this. We didn't use it last time. Let me go back to the beginning of our notes. Natural log and the number e. So we talked about the number e is this as it gets bigger and bigger and bigger. And that a natural log is a log base e. That's one of your extra credit questions as well. So that a natural log is a log base e. So we're going to use that in our problem. We're going to use the fact that a natural log is a log base e. Again, don't put the e in the line with, don't write the word log. It's the subscript is the e. E's a number. It's just like pi. Think of e like pi. Oops, going the wrong way. So when I see a natural log in a problem for us, whenever you see an ln, we're going to replace it with a log base e. And then I'm going to copy the rest of the problem of x equals 3. And now that I have a log, I have a base, I can rewrite this. So what's going to be the base of my exponential? E. And I'm going to raise it to the power 3 equals x. Now it says in your directions, in this part of the directions I will have, give the exact answer. So that's the exact answer, e to the third. Because e is an irrational number, so that's not going to be a nice number however we look at it. But e to the third is, this is exact. It also says, when necessary, use a calculator to obtain the correct answer to 2 decimal places. So now we want to find the approximate answer using our calculators. So on your calculators, if you have a graphing calculator, if you hit second, find my e, second and the natural log button, so second ln. So if you're graphing, you're going to do second, and then you see the button that says ln. And what should come up on the screen is e raised to the power, and it opens a parenthesis. So it already raises e to a power. That's very typical. And then you just need to type in your exponent here, which is 3. Close your parenthesis for good measure and hit enter. If you have the scientific calculators, I believe it is also second.
E to the x.
You have an e to the x?
Yeah, e to the x,
Yeah, it's on a second ln, brings up e to the x on those as well. I'm not like hiding calculators for me. The ones in my bag don't work. And on this guy, on your scientific ones that don't hold the display, you're going to enter your exponent first. So you would type 3 and then find that e to the x. You all have an e to the x. So it's just, again, second natural log. Yeah, it's 20-something. Can everyone get that from a calculator? So you will have this question on your test. We want to round it to 2 decimal places, so I shouldn't put an equal sign. I should put the approximately equal to. Let's do a squiggly. So you get, when you enter the 3, that's actually pretty much the same for everyone. You get 20.0855 and on and on and on. We want to round it to 2 decimal places. So we have 20.0. I see a 5 to the right, which means bump up that 8 to a 9. So there's 2 answers that you'd have on your answer line for this. You'd have the exact answer, which is e to the third, and the approximate answer rounded to 2 decimal places is 20.09. Is everyone able to get the 20.09? For 12.5, you're going to need to know how to do the e in your calculator as well. All right, C, log base 7 of 1/7 equals x. So what's my base? 7. What's the exponent? X. And that equals 1/7. Now we did these ones, this is the type we did last class. This is where x was last class. So 7 to what power gives me 1/7? Negative 1. So we know it's negative y? Fraction, 1 over. That 1 over tells us it's a negative. And then 7 to what power gives me 7? 1. So x equals negative 1. And then D, a log base x of 27 equals 3. So this is the last place I could put the x, which is for the base. So what does my exponential start with? X. It's a log base 7. Sorry, log base x of 27 equals 3. All right, so we start with our base, other side. So x to the third equals 27. So this is another one that we could probably think of. What number to the third power gives me 27? 3. Again, nothing is going to be outrageous. It's going to be small numbers like that we've worked with a lot. We've worked with that in our cube roots all the time. That's actually mathematically how you'd solve that. If I have a cube, the opposite operation is cube root. If I take the cube root of both sides, cube root of 27 is 3. But these should be things you could also look at to get your final answer. So E, I have a log base 64 of x equals 1/3. So I'm going to start with rewriting it. Base, oops, extra line on there. So my base is a base 64. Which one's the exponent? 1/3, thankfully, equals x. It's not a square root. 1/2 is a square root. Yeah, cube root. Yes, this is just asking for the cube root of 64. Or if you enter 64, and if you don't want to even think about that, if you enter 64 to the 1/3 in your calculator, we'll give you the answer. But yes, the 1/3 power is the same as asking for the cube root of 64. So what does x equal? 4. So either way, again, if you have the number and the power is also a number, just use your calculator to evaluate it. But it's great. We're starting to associate that 1/3 power with a cube root. It's an important idea. And last but not least, a log base 2 of 4x plus 1 equals 5. So I'm going to start with the rewrite. Base is 2. Exponent's 5. And that equals what I'm taking the log of, which is a binomial, 4x plus 1. What type of equation is this? I got quadratic, I got linear. What did you say, Napoleon? I got an exponential. I got a linear from Kevin. You seem pretty sure, Kevin. Why is it linear? Yeah, it doesn't have an x squared. Why is it non-exponential? The x isn't in the variable. So 2 to the 5th. 2 to the 5th is just the number 32. So that would be just something you grab from your calculator. If both the base and the exponent are numbers, evaluate. Equals 4x plus 1. Linear. So subtract 1 from both sides, so we get 31 equals 4x. Divide both sides by 4. X equals 31/4 or 428, 28.75. Not 28, sorry, 7. I'm thinking it goes into 28. Sorry, 7.75. If you want the decimal. But you can leave the fraction. It's fine. So any questions on solving our log problems or solving our exponential equations? All right, now I actually printed out 12.5 for everybody. Because it is word problems, it'll just save a lot of time. Because you don't want to have to write these word problems down. So who needs a copy of 12.5? So in 12.5, we're going to solve some exponential growth and decay word problems. And in every one of these word problems, you're going to either have this set up or have to put together this setup here. A equals A naught. That's how we read it down here. A naught, A with the little 0 on it. So A equals A naught. There's that number E. That number E, E is a number, is in our exponential growth and decay, and it has an exponent of k and t, where t is a time, and k is some constant that will be given to you. So k is a constant that you'll get. Time, we're going to have to figure out how long it's been since we started. So let's look at one of these problems, because it's a lot more intimidating looking than it seems. So the exponential models describe the population of Iraq, A, in millions, T years after 2006. So the only thing that I really get there for information is we're starting in 2006. So every time we figure out a time, we're going to say how many years it is from 2006. And then it gives us our equation. A equals 26.8 e to the 0.027t. What is the population of Iraq in 2006? So what we need to do is figure out how many years from 2006 we are. Well, if we start in 2006 and we're in 2006, how many years have elapsed? None. None. We're in our start date. So what would our time be? 0. How many years it's been since 2006? Hasn't been any years. We're still in 2006. So all you have to do in these problems for this class is figure out what your time is and substitute it into your problem. So I'm just going to put 0 in for t. And then it's just a matter of putting that into your calculator. That's what 12.5 is. Setting this up, putting it into your calculator. Now this one we could actually probably figure out by hand, because you always want to start, it depends on the type of calculator you have, but let's start by multiplying my exponent. What's 0.027 times 0? 0. So this is really, most of these you won't do by hand, but this is, so e to the 0 power. Well, what's e to the 0 power? So you got to evaluate exponents first, order of operations. What's anything to the 0 power? 1. We know that from our graphs. And I don't think I caught one person out of both classes saying something to the 0 power 0. I think they weren't here for the graphing day. And what's 26.8 times 1? 26.8. Here's a hint. A naught, that number out front, is always your starting population. So if you're ever asked for the population in the year you're in, it's always the big number, because the other parts will become 1. So when you look back, I didn't go over this here, but the original amount or starting population. So if you're in your starting year, that's your population. The A naught is. But then the other question is, what is the projected population in 2025? Round the projected population to 1 decimal place. Okay, so the only thing we're going to substitute in this class is time. So I need to figure out how much time has elapsed between 2006 and 2025. So all we're going to do is take 2025 and subtract from it 2006. And that's going to give us our starting year. So we've had 19 years pass. So that's going to be our time. Our time is 19 years, so you just go back to your equation. 26.8 e to the 0.027 times 19. And you can put that whole, if you have a graphing calculator or if you have one of these types of calculators that holds a display, you can put that in your calculator all at one time. If you have the other type of calculators, it's trickier. You've got to kind of work backwards. So if you're working with a scientific calculator that does not hold the display, you're going to start by multiplying these two numbers together. And then you're going to step back and you're going to find the E, and then you're going to step back and hit times 26.8. But most of you have this type or graphing, which put the whole thing in at once. You could type in 26.8 times, pull up your E. It's open those parentheses for you, so type in 0.027 times 19 and close the parentheses. But you can enter that all at once as 26.8 times E, 0.027 times 19, close parentheses. Put it in all at once. Unless you don't hold the display, and then you work backwards. Multiply, apply the E, multiply. Let's see if we can all agree on an answer for this.
Get the E times the 0.07 times 19. Are you supposed to times that with 26.8?
So you're going to find E to this power and then multiply this whole answer by 26.8. So try it, because you're going to have to do these on your own. What do we get for an answer? I have a 44. We went around to one decimal place, yeah. So if you have 44.8, one decimal place. Yep, it'll tell you in the directions on these. What'd you get? It should be 44.8. Is everyone getting 44.8? No. What type of calculator do you have? So you can enter the whole thing at once. So you're going to start with multiplying the exponents times, yep, 19. Equals, okay, now apply the E to the second term. And now multiply that by, so you're working backwards.
Okay, yeah, I just didn't know how to like put it in there. Thank you.
Anybody else find
Oh, so it's
44.8? So start by multiplying. So is this what you get? Did you get it? Did you get it? Alright, so we can enter.
Bless you.
Yay or nay?
Nay.
Okay. Perfect. But you want it, so you do 26.8 times your E. There's not automatically. So 26.8 for your E, and then just write that as times.
So the parentheses times.
Yep. All right, so once we get the calculator part down, all these problems are just putting it into your calculator. So for B, complete the table around the projected population to one decimal place. Now you notice this didn't give us an equation. But we know the general setup for the equation. So we're going to have to start by putting the equation together ourselves. And this is, you have this table on your homework, which is why we're doing some problems like this. So we have our starting population. So our equation always starts with A. What's the first number in our equation? That A naught stands for which number? Yeah, the starting population. So this population, since we're starting in 2007, this is going to be our A naught. So this is going to be, if you're ever given an original population, that's where you start. And then it's always E. So let's write, we're looking at A equals A naught E to the K T. So our starting population, E. And then what's K in this first problem for Madagascar? This is really two separate problems. 0.285. See, it's population and projected growth, and it tells you right there it's K. So we have 0.0285, and I'm going to write this a little differently so we don't get confused entering in our calculators. Now, our projected population, we're looking for 2030. So we need to figure out how far that is from our starting time. So what's our starting year? 2007. So to figure out what T is, all we have to do is take our 2030 and subtract 2007. See how many years it's been. How many years have we been? 23. So in your exponent, again, I'm going to write this a little differently, maybe to avoid some confusion when we enter it into our calculators. So it's going to be times 23 years. So it's a calculator problem. This one we had to set up first, but then it's just put it into our calculators. So try that 19.4 times e to the 0.0285 times 23. And what do we get for a population in 2030? To one decimal place. 37.4. Is anyone not getting 37? You should get 37.3664. No. Everybody able to get that from your calculator? And these are nice, easy problems. Just put in your calculator. All right, 2, we want to do the same thing for Bulgaria. So for number 2, you put A equals, and what's our starting population of Bulgaria? 7.3 E, and then we're going to multiply. This time, our population is going down. That's what it means when it's a negative. Negative 0.0082. And we're looking again in the same year. So in the same year, how far are we, 2030, from 2007? 2030. So we don't even have to figure it out again. We just got new numbers to enter into our calculator. So we have 7.3 e to the negative 0.0082 times 23. So we would expect this to be smaller than 7.3 million since their population is declining. So what's my population in 2030? You got 8.81. You probably forgot a negative sign. We shouldn't be getting bigger. Yeah. Population. Got 6. 6.0. 6.04. Yeah. It's 6.0. We just write 6. You do get 6.0452, but run one decimal place would be 6.0. Questions? So we're out of time for the full classwork, but we certainly have time that you could do the last one. So an artifact originally had 15 grams of carbon-14 present. The decay model, A equals 15e to the negative 0.0001 t, describes the amount of carbon present after t years. How many grams of carbon-14 will be present in 7,125 years? Notice it's set up a little bit differently. It didn't give us a start time and an end time, but it did just tell us. It told us explicitly how many years have elapsed. So your T is the 7,125 years. So see if you can find how much carbon-14 is present, just knowing that we're 7,125 years in the future. All right, how much carbon-14 did we have present in 7,000 years? Yeah, we're going to have about 7, again, I didn't tell you to round, I'll do 2. If you said 7.4, that's fine as well. But about 7.36, what are we looking for, grams. Did you multiply these first and round? Possibly? Let me look at how you entered it. So, any questions? 12.5 is nice, just throw it in your calculator. So make sure you really focus as well on that 12.4 homework this weekend where you solve the exponential equations, because I find people miss that most on the test. You have your review now, so start looking at the Unit 4 material as well.